In the first hour, we're going to go over mirrors and lenses and how to work with them, how to understand where the images are. We all use images and we use lenses all day long. We call them our eyes. In the first thing we're going to do, since yesterday we talked about mirrors. And whenever you're doing problems like this, and in the test you will have you will get either a mirror or a lens, and the question will be something like, you have a mirror, it is converging, it's converging 5. The object is, hold on, let me see, 25. Let's make it 30 centimeters away from the mirror. And then what I want to know is, where is it? What kind of image is it? And we'll go over the varieties of descriptions and draw a 3-ray diagram for this. In the test, and we'll talk about the reason why I'm going to do 3 here, you're going to do only 2 rays on the test. It's not, it's a bit overkill for the 3rd ray. In homework, you do the 3 rays because you got a lot of time. In the test, it's a little bit limited. Whenever you're doing problems like this, where I'm saying draw a ray diagram, what's the first thing you do? You don't draw a ray diagram, not just yet. You do the math first. Now, the one thing that I will do is start to set this up. I need to set up an optical axis. So what I'm going to do is, actually, hold on. I didn't even follow my own advice. You should do the math first regardless of what's going on. So you take 1 over F, 1 over I, 1 over O, solve for image, 1 over F minus 1 over O equals 1 over image. So image is equal to 1 over F minus 1 over O. And you get that. Objects are to the left of whatever is set up. So to be, I'll just say left of. The way that everything is set up is that the objects will always be left of the mirror or the lens in single lens setup, or single mirror or lens. It's definitely left of a mirror, because if it's to the right of the mirror, it won't reflect because it's behind the mirror, which is kind of a nonsensical way of arranging a mirror and an object. Yesterday we talked about diopters. So I have a converging mirror 5. I talked about this with my optometrist, and I asked him about this, and he said, yeah, that's a valid way of describing the image. It is a converging mirror. Why? I said so. So the focal length of a converging mirror is positive or negative? positive. Anything that's converging, regardless of the fact if it's a mirror or a lens, if it's a converging mirror or a converging lens, its focal length will be positive. So this focal length is positive 1/5 meters, or 0.2 meters. And the unit that we'll be using in ray tracing situations is we'll be using centimeters. Centimeters is something that we can all wrap our heads around in terms of placing the object. When you're in that thin lens lab today, you'll be doing everything in centimeters. And the thing that I want you to do before you even start moving this stuff around is think about the math. Get the math done first. Get the math done first. This is 1/20. The object is 30 centimeters away, so that's 1/30. And we invert. So this gives me 60 centimeters. And it's positive. The image distance is positive. For a mirror, if the eye is greater than 0, images left of mirror and real. So the image that we have is positive. It's a positive 60 image distance, which means the image is definitely to the left and it is definitely real. Real means that the real light rays pass through where the image is located. If it's a virtual image, we're talking about the dotted lines, the traceback rays. So we know where this thing is. The object is 30 centimeters, or object is 30 centimeters to the left. The focal length for a mirror, if f is greater than 0, f is to the left. F is to the left. The other thing that we need to do is we need to figure out the magnification of the object. The magnification is negative I/O. That means it's negative 30. The image, whoa, back up. Image is 60. Image distance is that. The minus sign gets rid of that. And the object distance is 30. So the magnification is -2. The absolute value of the magnification is greater than 1, so it is enlarged. The M is less than 0, so it is inverted. So what's going to happen is that we're going to draw an upright arrow as the object, and we're going to, this changes physically. It's not physically, the image isn't to the right, but I'm just showing you what it looks like. Physically, the image will increase in size, and the image will appear upside down. The first thing you do, and this is a reminder, and if I'm reminding you, then this has to be important. Don't even draw these ray diagrams until you get magnification, image distance, and all of the different image, hold on, let me practice on a this and see which color shows up best. Let's just underline. That's not going to work. So to describe it, it is left of mirror, real, enlarged, and inverted. Those are the 4 qualities that I look for. When I want an image, I want real, virtual, left, right, enlarged, reduced, and inverted or upright. So real, virtual, left, right, enlarged, reduced, inverted, or upright. And so this gives you, those are the facts of the image. So we have basically done all the numbers and identified all the descriptions of what's going on. This should be an image that's to the left of the mirror. It should be inverted. It should be enlarged. So now we can start drawing, where did that come from? Drawing the image and the object. The first thing I do is I draw the optical axis. The optical axis is the main horizontal line. The line passes directly through the lens. Now comes the choice of, well, I gotta figure out, now this is where there's a little bit of artistic expression and it's not quite precise. I know the object is to the left of the lens. I know the image is to the left of the lens. I know the focal length is, of the mirror. The focal length, object, and image are all left to the mirror, which means the mirror should be the most far right thing we got. So what I typically do is I give a little bit of a gap on the right-hand side. It may be useful. And then I draw this. This is the mirror axis. Now, when you do this on the test, I'm mainly interested in, were you able to get close with drawing the image correctly? I'm not looking for really precise images or pictures. The next thing I got to look at is I got to choose what's the construct? I'm trying to think of the right word for it. What's furthest away from the mirror axis? Well, that's the image, and it's at 60 centimeters. So I gotta pick a horizontal scale. If I do 10, 20, 30, 40, 50, 60, that's fair enough. So 10, 20, 30, 40, 50, 60. I may on the test make available, I'll make copies of graph paper so you can do it. If you have a normal sheet of paper, if you had a blank sheet of paper, what I would do is I would choose that as 10 centimeters. And I think the scale of this is about, yeah, it's about right. Or you could choose 1 centimeter on your regular ruler to get the same thing. So I physically place the image here. I don't draw it quite yet. I know my object is 30 centimeters away, so I draw my object. I know my focal length is at 20, so I draw the focal length there. Now, if it's useful, a lot of times it's not even used. I mark F prime. It's not going to be used in this case. And what I do now is the magnification is -2, which means that the image is going to be larger than the object. The object will be half the size of the image. So what I do is I pick something that I can easily convert and make the image big enough, but not too big on the page where it scrolls off. So I'm going to make this 6 blocks, 2, 4, 6, which means that the object is 3 blocks up. So if the object is 3 blocks up and the magnification is -2, I should have -6 blocks, which is how I've drawn this. This is the reason why I draw this after the math. I don't even draw a ray until I have everything labeled and the object in the image physically drawn out. Because if you physically draw this stuff out first before you even touch a ray, your rays are way more probable of going through correctly. The first ray, the easy ray, I'll draw that in blue again. The 3 rays, let's see, this space isn't being used, is all 3 start at tip. What's going to happen is that there will be 3 rays from the tip of this object, and they will all focus at that image point right there. And what this will show is that, yes, an image is there. The light rays coming from this point will focus at the point of this image. The first ray is through middle of mirror. And the way that it looks like is you draw a line from the tip of the object to the center of the mirror. Now, technically, the mirror looks like that. But it's very difficult to draw this thing accurately. So what I end up doing is I just draw a flat plane. It's the easiest way to do it. We're not that good in drawing ray diagrams with a curved mirror. Now what happens is, if this ray was to continue its merry little way, but it's a mirror, so this is a virtual ray. Any light ray passing through a mirror or a lens is unbent. This ray is reflected, but it is not bent in an odd way. It's as if it hit a plane mirror. So the ray looks like that. And if you were to measure, if you were really to measure this angle and that angle, the law of reflection says that they should be equal. And I've taken protractors out before and taken a look at it, and it's really close, within error of me being not an artist or an engineer or an architect. I mean, they should be able to do it, but not me. The second ray is parallel beginning then passes through F. We've seen yesterday the descriptions and the differences between concave mirrors and convex mirrors. The concave mirrors will take parallel light and send them through the focal point. So light that heads straight at the mirror, if it was to go on its merry little way, the virtual ray would do this. Now this is the interesting thing, and now you can start seeing these rays start to line up. If you connect the contact point with the mirror to the image, what is in between the focal point? Now granted, I draw like a barbarian, so it's not going to go perfectly through, which is fine. But it's good enough. I have no problem with that ray being drawn like that. The third ray is a tricky ray. This is why. Now, draw these two on the test, move on. In terms of test quality, this is what the graders look for. This is what I look for. I look at that magnification and I see -2. I look at the image distance and I see +60. So your professor is going, this thing should be left, inverted, and enlarged. Had you drawn this image over here for a mirror, where you got a +60 image distance, I would have problems. If you drew this image upright, I would have problems. If you drew it reduced, I would have problems. What you drew does not agree with the number that you determined. So you either got the math wrong or you were bad at drawing. That is what I'm looking for. The majority of the points, in my opinion, I'll have to talk to the grader about this, is to get that number and describe this. How I would just go real, left, enlarged, inverted, and just circle them, or I would just write RLEI and just leave it like that. The last ray depends on the situation. What I've done is that when you look at the lens or the optics file that's on Blackboard, I go through all the permutations. I go through all the ray tracings. The third ray goes through F or F prime and becomes parallel. So the big 3 points of ray tracing: first ray through the middle, second ray starts parallel, third ray becomes parallel. First ray through the middle, second ray starts parallel, third ray becomes parallel. So this, and actually how I do it, this is how Dr. Eschenberg kind of cheats it, is I know where this thing is going. It has to. It's physics. So I draw the parallel line first to show, yep, there it goes. And then what I do is I then look at the orientation of all this and I go, well, what 3 points line up? Object tip, focal point, mirror contact. And then I draw that. And so that is the drawing for this particular orientation. I've got a converging mirror. I have an object to the left of the focal point. There are situations where the object is to the right of the focal point, and that will change where the image is. What I'm going to do now, I'm going to give another 30 seconds so that everybody can take a look at this or take pictures or do whatever. Yes?
So, are those the 3 rays that we'll have to draw in like any kind of picture?
I would say that you can pick 2 of 3. In the test, in the problem set, I want you to do all 3 for practice. On the test situation, you get to pick 2 of the 3.
Okay.
The 2 that I would pick, because I'm as lazy as you guys are, I would pick the green ray and I would pick the red ray and just move on. Some people would, blue and then red, not green. If you want to draw the 3rd ray, fine. It's not required. I don't think I'll give bonus points for it, but it just allows you to be thorough and see how it all lines up. Next, one of the things that I will note for this is converging mirrors can have real or virtual images. They'll either produce real images or virtual images, one of the 2. It really depends on where the relationship of the object is with the focal point. The next one that we're going to do is I want a diverging 5 mirror. Now notice there is no, and this is one of the things that I talked with the optometrist about. I said, I'm not going to use a positive or negative sign on occasion. What I'll do is I'll say, you have a diverging mirror 5. What does that mean? And he looks at me and goes, well, you've got a -5 diopter mirror. It's a mirror. It's a diverging mirror. Therefore, the focal length must be less than 0. It must be negative. So the focal length is -1.5 meter or -20 centimeters. And that is that. What I'm going to do is I'm going to say the object is 20, no, not that. Ooh, that would be bad. 30 centimeters to left of mirror. And then we'll do the usual jazz. Where is it? Describe it. And then draw a 3-ray diagram for it. So we're not, in effort to speed things up, I'm just going to tell you the question. First thing you do is you have F. What am I doing? All right, hold on. F inverted, I inverted. You can draw it like this, O inverted. It's the same thing. F inverted minus O inverted equal to image inverted, or F inverted minus O inverted is equal to I. So I is equal to minus 20 inverted minus 30 inverted. So the image is at -12 centimeters. This is for a mirror. The image is negative. Therefore, the image is virtual and it is to the right of the mirror. So these are the big 2 that we need to figure out, or that we've just found out. Magnification, negative I over O, which means this is negative 12 over 30, which means that magnification 6 over 15, or, not that, 2 over 5, or 0.4. So the magnification is positive 0.4, which means that this thing is reduced. Magnification is less than 1, or the magnitude of the magnification is less than 1. It's positive, which means it is upright. So it's going to start like this and then end up smaller, but still upright. So we have everything that we need in order to draw this. Now we've got a little bit of a different situation. The image is to the right of the mirror. The object is to the way to the left of the mirror. The focal length is between the object and the lens. We still got to do the basics. We place our optical axis right down the middle. Now I got to make a choice. I'll take the furthest to the right and say that the furthest to the right is that guy. Focal lengths less than 0 for mirrors are to the right of the mirror itself. So the one that's furthest to the right, the image is 30 centimeters to the left, then we have F prime, then we have the mirror, then we have the image, and then we have the focal length. So the focal length, I'm gonna say is, I'm gonna need a little bit of space, I think, here. Now I need to pick a scale. I'm gonna pick, hold on, 30, let's see, 10, 20, 10, 20, 30. Okay, so what I'm gonna do is I'm gonna pick 4 blocks per 10 centimeters. So that's 10 centimeters, 0 centimeters, 10 on the left, 20 on the left, 30 on the left, 40 on the left. How you pick your scale is kind of personal choice. How I tend to do it is based on how much space do I have physically on the page. That means that this is my mirror wall. The mirror is like that. Object is 30 centimeters to the left of the mirror. So the object is there. If that is F, F prime is there. The last thing I need is the image distance. It is negative 12. So it should be just a smidge left of here, because each of these blocks would be 2.5. So that is the image. The image is upright and reduced, which means the object is going to be the biggest thing on this, or the bigger of the two. So what I do is, since it is a scale of 0.4, I'm gonna make it, it's either gonna be 5 or 10. Let's make it, we don't have enough room for 10. So we'll just make the object like this. The image distance is 0.4, which means it will be 4 centimeter or 2 blocks tall. Ooh, wait, hold on. I drew it 6. Hold on. 6 times 0.4. 2.4 blocks is what I need. I drew it off to scale, but I recovered. Doesn't have to be precise. It looks like more like 2.5, but we can live with it. The first ray, the easy ray, is a ray that if it passed through, it would just go like this, onward. But what happens is it reflects, and what happens is the light goes like this, and then we trace back to that point. So this is the dotted line following this ray, if it went straight. This is the trace back ray for the reflected ray. It's like that. The second ray is the parallel ray. It starts like this. It starts parallel. In a, I'm just gonna go back to this real quick. In this situation, parallel rays converge like that. They all focus at the focal point. For diverging mirrors, the parallel light bends away, but if you traced it, the traced ray or the dotted rays travel back to the focal point. So that ray reflects away from the focal point, and you get that. Now the third ray, as I've said before, is tricky. The one thing that I do know is the ray itself becomes parallel. And so what I tend to do is I draw the parallel line first. The trace back ray looks like this, and then the ray does that. So that's the reflected ray and the reflected ray trace back. And once you see what the ray does, you can see how it goes. This ray is aimed right at the focal point on the other side. So the ray is like this. It's aimed at that focal point. So for the third ray, a ray aimed at the focal point becomes parallel. And then you trace that ray back. So all three of the trace back rays, all three of the reflected rays that are traced back, they all converge at that one point. Now granted, no light physically passes through that point, it's just a mathematical construct. But all the rays line up to go through that. And so those are, now there are two more types of mirror alignments, but we're not going to go through it because we just don't have the time. I will say, before we move on to lenses, this has all been done really on that optics handout. In the optics handout, there's kind of a study guide for mirrors and lenses. Objects are always to the left of the mirror or lens in singular mirror and lens orientations. Object distance is always positive. For a mirror, if the image is to the left, the image distance is greater than 0 and real. Oops. If the image is to the right of a mirror, the image distance is less than 0. For converging mirrors, the focal length is on the left, and the focal length distance is positive. For diverging mirrors, the focal length is negative and the focal point is to the right. And so that's the general setup of the object, image distance, and focal points for mirrors. We've already covered that. For lenses, a couple of things flip. For diverging lenses, the focal length is less than 0, but instead of now being, it's still a diverging lens is like a diverging mirror. Their focal lengths are both negative, but a diverging lens has a focal point that is to the left. A converging lens is to the right, and its focal point is greater than 0. So to show the mirrors converging is like this. The rays all go through one point. For a diverging mirror, they all converge there. For lenses, a diverging lens looks like that. The rays will pass through rather than reflect. And so what happens is, if you trace back those rays, much like you trace back these rays, the focal point is to the left. For a converging lens, which is what most people think of as a lens, that light ray all focuses at the same point. Now, in both of the cases, diverging is always negative, converging is always positive, but the image distances, if the image distance is less than 0, it is to the left. It is left and virtual. Virtual images from mirrors are on the right. The light never passes through it. Virtual images for lenses, because the light passes through the lens, a virtual image is to the left. If the image distance is greater than 0, it is to the right and real. both lenses and mirrors use 1 over F, 1 over O, 1 over I, and M equals negative I and O. And lenses use M descriptions exactly like mirrors. So if you have a magnification of -2, regardless of it being a mirror or a lens, -2 implies that it's been inverted and enlarged. Positive 0.5, it is upright and reduced. Negative 0.2, it has been inverted and reduced. So you could sit there and go, and a lot of the multiple choice questions that we have are like this. DeRocher, your magnification is -5. Tell me, is it upright or inverted?
It's negative 5 and
So is the magnification, is it upright or reduced? It's -5. Wow, DeRoe's not here. I'm very upset. He's the one, Mr. Perfect. Who knows? -5, magnification. Upright or inverted?
Would it be upright?
It's -5. So it wouldn't be upright, it would be inverted. Also, the fact that you said it as a question instead of giving it as a confident and, dare I say, slightly indignant answer, I'm a little bit disappointed. I wanted a little bit of how dare you ask such a simple question in your voice. So magnification -5. It's negative. It's got to be inverted. Its magnitude is greater than 1, so it's enlarged. You can get so much information out of that number. What I'm going to do now is we'll do a conventional convex lens, which is a lot like what you guys do in... Oh wow, I'm out of oh well, I'll flip it. Oh no. So we have a lens. It is a converging comma, let's just keep it normal, 5. Converging 5. A converging lens means that it must have a focal point greater than 0. The focal point is the inverse of that. Its unit is diopter. I've seen both D being used, like 5D, or you just see 5. And when you're dealing with a lens or a mirror, that 5, you know, is its focal length in diopters. So the focal length is 1/5 of a meter, or 20 centimeters. The object distance is, let's just make it 30. So this is similar to the problem here, but what we've done here is, oh no, it's not similar to that. It's similar to this. Instead of having a converging mirror, we're going to have a converging lens. So image distance is 1 over F minus 1 over O inverted. This is 1 over 20 minus 1 over 30 inverted. And that should give me positive 60 centimeters. And the magnification, negative I over O, so it is negative 60 over 30, or negative 2. So it is to the right of the lens by 60 centimeters. Positive image distances mean it's to the right of the lens. It is a real image. You can actually take a piece of paper and focus an image on it. It is magnified. And it is inverted. Those are the big four descriptions that I'm looking for. So we now know where this image is. We know where the object is, all within relationship of where the lens is. And we know what the shape of the image is going to be. It's going to be a bigger image and it's going to be an upside down image. So we first draw our optical axis. I then got to figure out where am I going to put all this stuff. Image distance is at 60. So I'm going to put the image distance here. It looks like 2 blocks per 10. 1, 2, 3, 4, 5, 6. And that is the lens wall. So that the image is positive 60. It's a mirror. It's not a mirror, it's a lens. So whereas a mirror reflects light to form an image, the lens passes through light. You can see through a lens, but the light that you see in a mirror is the reflection of the light that hits it. My focal length is 20, which means that the focal point is to the right at 20 centimeters, which means that F prime is to the left and at 20 centimeters. The object distance is 30. So we put the object here. Now the magnification of the image is 2 negative, which means I'm going to do something like this. In fact, let me draw a little bit better. Okay. So the image distance is like that. The object is 1/2 of this. So the object must be 5 blocks tall and like this. When we look at the rays for the mirror, all of our solid rays were to the left of the mirror. Why? Because the rays were reflected. Yes?
What determines what side the object is on?
It's whatever I say it is, and in order to be consistent, I will always put the object to the left of the mirror or the lens, and the object distance will always be positive. There's only one specific case where the object distance is negative, and we're going to get to that next. But if it's a single lens or a single mirror, which is what you're going to get on the test, the object will be to the left of the mirror or the lens, and its distance will always be positive. Your question.
So the height of the object, is that simply a ratio? Just relative?
It's a ratio. Yeah, I don't like defining the heights of the object or images because it gets in the way, it could get in the way of drawing it on the page. All I'm interested in is that this thing is twice the size of that. And I tend to draw the larger of the image or the object way bigger because I think it tends to be a little bit more forgiving in terms of drawing the rays. The first ray, the easy ray, it passes through the center of the lens, and with the geometry of the lens, the light ray simply passes through the middle and is unaffected by the lens. When you really start thinking about what the lens is, it is refraction occurs, and it's because the index of refraction of the material is greater than that of the surrounding environment. So what's really interesting, and this is one of the questions on let's see, on the lab, if you have a water tank and you have a convex lens of air, the index of refraction of air is less than that of water. And what happens is parallel light diverges. If you invert the substances where the higher index of refraction is on the exterior rather than what is usual for the interior, convex lenses will act like diverging lenses because of the material. It's because if you go from water to air, the light bends one way. If you go from air to water, the light bends the other way. And so it reverses the behavior of the lens. So diverging air lenses in water, or concave air lenses in water, will act like converging lenses in air. It tends to freak people out when they see it. But it's just geometry and refraction and all that stuff. The second ray, it starts parallel, and parallel light on converging lenses bend toward the focal point. The third ray, that's a trippy ray. I don't like the third ray. Third ray and I have not get along. But now that I've figured out really the trick to third rays, is that the ray becomes parallel, that third ray. And what's really weird, I haven't even tried this. I've studied it from time to time. In certain situations, there's a fourth ray. We're not even going to talk about it. I shouldn't even be telling you that there's a fourth ray. But the third ray, when you look at this just drawing it parallel just makes the third ray way more obvious. The third ray, that light ray passes through F prime. Finally, we get to use F prime. And then the light becomes parallel. So those are the three rays. And what's interesting about this is that the convex lens in this particular setup, we used to do a lab, we just ran out of time or we just got tired of it. Also, we used to do optics of the eye as a lab, and we had a little eye tank filled with water, and we had different lenses, and we would put images up to it and you would describe the image. But let me tell you, when those labs get set up on Monday, and on Thursday afternoon, it's the same water in the eyeball, it looks a lot like they have serious glaucoma, and it's just hazy and nasty water, and we just got rid of it. But when you think about it, the eye is a big physics experiment. You've got the lens, and if you're looking at a tree, that lens ends up being convex. And so what happens is that the image ends up on the back of your eyeball inverted. So that if you were to physically look at where the photons of the light coming from the tree in the distance, the top of the tree is actually at the bottom of your eye, where the photons interact with the cones and the rods to produce the information. which is really interesting because right now we all perceive the world as upright. So if the eyeball actually sees everything upside down and we perceive as reality as being right side up, what happened? It's a software correction. Your brain knows that it's looking at everything upside down. So what it does is, in your mind's eye, what we see, it flips everything upside down to what it sees on the back of the eyeball, which is right side up. Interesting experiment that was done in the 60s, and they do it from time to time. They have special goggles. The goggles invert the light. So the goggles make your eyeballs see the world is upside down, which is then put on the back of your eyeball as right side up. And since your brain is always having to invert that image, you see everything upside down with the special goggles initially. So you put the goggles on and the whole world looks upside down. What happens after a couple of days of wearing the goggles and you repeatedly bumping into things is your brain figures it out and it flips it for you. So eventually there comes a day where you see everything upright normally with the goggles. Now this is the trippy part. When the experiment ends and you take off the goggles for about 20 minutes before your brain goes, wait a minute, you're messing with me again, you see the entire world upside down without the goggles. What you're seeing is that what you're watching is your brain taking a look at the software and flipping everything back over again. And once it realizes that it's gone back to normal, it will correct itself. It is very interesting how the brain and physics works together. So, I like it. The big part, now what they're gonna do in class, or not in class, we're in class, in lab, is you're gonna do lenses, convex and concave, get the images working and stuff. You're gonna play with a few things. One of the things that you're gonna do is, for a convex lens, you're going to determine the focal length of a convex lens. Let's see, 3, 7, 9, 10. Just over half. So you determine F of a convex lens, and how do you do this? Well, what you do is you set an object that has an O that's much greater than the focal length. So you're gonna have, what you end up doing is you take, what we've done before is you step outside the lab, you hold the lens up to the lab door, and you focus the image of the door facing Brevard on the wall. And so what you'll do is you'll see an image of the opposing door on your door. And what you do is, if the object distance is much greater than F, 1 over O becomes 0. So this becomes that. And what you do is you measure the distance from the lens to the wall, and that becomes your focal length of the lens. That's how you determine the focal length of the focal length of your lens. just as a reminder, the focal length in lab should be positive or negative 16 to 20 centimeters. Those are the typical focal lengths that you've got for lenses or for the lenses in the lab. You won't be dealing with mirrors. So you should be getting answers of 17, 18, 19, 20 centimeters. Some maybe 21, I'm not sure. But in that range. If you end up with a focal length of 200 centimeters, you've messed up. The compound lens is a major part of the experiment that you do today. What you do is it helps you determine the F of the concave lens. There are in the, you should be effectively ready to do all of the problems in problem set 7, with one exception, the compound lens, and we'll be doing it. Wait, do we have compound? Yeah, it's the first problem. You're ready to do everything except for the first problem, and we're about to do it right now. The general overview of this, in a compound lens, it is a problem that typically, I just don't have the room to put a compound lens problem on test 3 because we got to be dealing with mirrors or lenses and doing the ray diagrams. So what typically happens is on the test, you get the lens or the mirror, and then on the final, you get the compound. Now, compound just means multiple. So part 1, you have object, convex lens, and then you figure out, you find I. And this is the lens that you use outside in the hallway, so you know what that focal length is. What I'm gonna do is I'm gonna use the numbers. I'll let you guys use the numbers in the problem set. What we're gonna do is we're gonna use the lens from here. If that object distance is 30, then this image distance, which is not to scale, is 60. And its magnification is -2. And I'm gonna use M1, O1, and I1 because this has an F1 of positive 20 centimeters. So this is the math, if you want to see the math, it's this right here. And that's the first part. What happens here is the object is still at the same place. It is still the same distance from F1. This is still I1, but what I've done in between is I've placed a concave lens in between the image and the first image, I1, and F1, and it's going to be a diverging lens. And the distance between the two is called D. So you're going to have two lenses. This is the distance O1, just to write it again, this distance is I1, that distance is D. And this is the most critical sentence of this problem. You treat the image from the first lens as the object of the second lens. You treat the image from the first lens as the object of the second lens. You treat the image of the first lens as the object of the second lens. There, I've said it 3 times, so it must be really important. What you do is, this is your image distance I, and you've placed a concave lens in between. This distance here is what we call O2. That image over here is now the object for this new lens. So if I1 is equal to 60 centimeters, and let's say D was equal to, I need to make this work out. Hold on. I'm gonna make the distance, I'm just gonna say, play the math. 30 centimeters. Therefore, my new object distance is negative 60 minus 30 centimeters. So if it is 60 centimeters from there to there, and that distance is 30, then that distance has to be 60 minus 30, or 30. Remember when I've said in single lens mirror, the object distance is always positive. In compound lenses, the second object distance may be negative. I've done these problems where the this image is to the right of this concave lens, which means this object distance is negative. If the image was here from the first, the new object distance would be positive, because the image from the first becomes the object for the second. The object is to the left of the concave, so it is a positive object distance. So you have to know where it is and with relationship to the lens. Now what you do is you run the math again. I2 is 1 over F2 minus 1 over O2, inverted. The focal length, oh, I gotta pick a focal length for this. This is the part that makes me worry. I'm gonna make it negative 40 centimeters. I think the math will work right for that. So this is 1 over negative 40 minus 1 over negative 30 inverted. And that will give me a positive image distance for sure. And that will give me a positive image distance of positive 17.1 centimeters. So to draw this thing out, I want to draw this this a little bit more. Just, whoa. Oh, hold on, I didn't take the negative sign. Oh, excellent. Okay. $120 centimeters. When you do these compound lenses, I do not expect ray diagrams to be drawn. In problem set 7, the first half, the one that involves only the convex lens, I do have you draw the ray diagram just for the practice. But when you're doing the compound lens on the final, I don't want a ray diagram. It's unnecessary. Also, ray diagrams for compound lenses are just nightmares. So I just don't deal with it. But what I'm going to do is I'm going to draw out the axis and show you what went on. Here, I have my object here. That's my image. Or I'm sorry, not object. That's my object. The object is 30 centimeters to the left of the convex lens. So 1 block per 10 centimeters. So that is F1. The image from the first lens is 60 centimeters to the right. And so that distance is 60. That distance is 30. The focal length of this guy is 20. So F1 is there. And so that distance there is 20. What I did is I put the concave lens here, which is 30 centimeters. That right there is D. Now this is O1, that's F1, that's I1. And if this distance is 30, then this distance is O2, and that is negative 30. Because the object, the image distance is now the object distance. It's 30 centimeters to the right of the concave lens, excuse me. So it's negative 30. The image distance from 2 is 120. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so I2 is there, and I2 is positive 120. That is negative because O2 is to the right of concave. In 214, O2 is the only time in all these lenses stuff that O2 could be negative. And what I try to do on the it's not useful in lab to study a virtual image. If it's virtual, you can't really look at it, so it's not very happy. It's not a, you just can't deal with it. So we try to set things up so I2 is greater than 0 and real. It's something that you can see. Because what's going to happen is that you're going to set all this stuff up, and then you're going to put a screen right there, and there's going to be an image. There's going to be a light. And what they do is in the optics lab, the image distance, or the image, excuse me, image looks like this. You've got a vertical arrow, and then you got a horizontal line with a circle. So you can tell if the image has been either inverted, or we don't really study it all that much, if the image has been inverted in the horizontal as well as the vertical. So you can tell, but generally the one that I'm interested in is this guy right here. So now we know where this thing is. Let's describe its describe it. I2 in this case is greater than 0. It is right of both lenses and real. If both are negative, it's virtual. If I2 is less than 0 and I1 is greater than 0, it's still virtual. It must be to the right of both lenses. Lenses? Lens? I don't know. This is not English class. I don't care. So that I2 has to be positive. I1's definitely going to be positive. I2 has to be positive as well. So if I2 is positive, you know you're dealing with something to the right, it's real, everything is fun. The M2 is negative I2 over O2. I2 is, what did I say I2 was? 120, so positive 120. O2 was negative 30, which means this is positive 6. That magnification 2 is positive 6. Positive 6, oh, I made a mistake, thank you. Or I meant to do that, yeah. All right, positive 4. There was one time in class, I was actually getting mad because I was like, I don't understand. Negative 1 times negative 1 is negative 1. How obvious why can my students not see this? And then a little neuron just started going off and going, oh, dude, this is bad. Excuse me for a second. And then reality took over. So it is positive 4. All right. So M2 is only useful to determine total magnification capital M. Capital M is the final magnification. Capital M is the magnification that determines the image overall. Capital M is M1 times M2. So this becomes -2 times +4, which is -8. So in our final description, it is to the right, it is real, it is magnified, and it is inverted. And what's going to happen is you're going to, in lab, you will not have F2, you will solve for F2. So this is just merely in lab, you will know, not co, know I2, and then you will solve for F2. So in the lab, you'll get this thing to focus. You'll measure that distance, and that's your I2. And then once you got I2, then you can solve, then you could go through the algebra to get that F2. So let me look through this. So what we've done is we're fully prepared for problem set 7. Technically it's due tomorrow. If you want to turn it in first thing Monday, I mean, granted it's a little bit late, but it'll still count. And what we're going to do is on just an outline, and then I'll cover, there's one thing that I am going to cover just so that I can knock it out fairly quickly. Tomorrow we will cover single slit, double slit, diffraction grating, and these are all of the subject called diffraction. We will cover polarization, and technically tomorrow is a review day because we're off of, oh my goodness, we're covering a lot. And thin films. So we gotta kind of book it tomorrow. But the one thing that I do want to cover is light when thought of as a wave can interfere with light. It can interfere with itself, it can interfere with other sources of light, and we are aware of constructive and destructive interference. Constructive and destructive is when you have two waves. If we're just thinking about light as two waves, the two light rays will, if it meets peak to peak, you will suddenly get a huge peak, and then the two waves move away. And so this is similar to, they talk about in the Atlantic, Gulf of Mexico, stuff like that. They talk about rogue waves, and what happens is the ocean is not flat. It is this big cacophony of just waves traveling all over the place. And sometimes you're in the wrong place at the wrong time, and waves will converge at one place, and you'll get these insane waves that will just toss your oil tanker around, and then it'll just disappear and everything will be fine. You're like, what is that? That's the convergence of many waves coming together at the same time at the same place. You can also get it from two troughs together, and it will make, it'll make a bigger trough, and then the troughs go their merry way. So that's a weird smiley face, but the troughs can merge and form a bigger trough. The peaks can come together and form a bigger peak. In destructive interference, that's when you have a peak meeting a trough, and for one brief moment you get nothing, and then the waves, oops, not you, you get that. So the peaks can come together. And the one thing that we'll talk about, we're familiar with energy, which is measured in joules. So kinetic energy, energy from the sun, that kind of thing. There is another concept called power, which is 1 joule per second, and it is called, what we're more familiar with, it's called a watt. And then the last one is intensity. So power is energy over time. Intensity is power over area. The amount of power distributed over a particular area. And we just talk about it as watts per meter squared. And I think they call it like a candela or something like that. But I tend to use watts per meter squared. That's how I think of it. And the biggest thing about intensity that you can think of, take a magnifying glass. What does a magnifying glass do? It's a convex lens. It focuses all the energy of the sun that hits that disc and focuses it on a small area. So the energy that I have in this coming from the lamps through my fingers in that area is not sufficient to burn my hand. The power is distributed over a wide area. But if I had if my fingers were instead, there's now a convex lens between my fingers, let's just admit it, we've all taken a magnifying glass and just burned the snot out of ants or whatever we can find. Well, why is that? The power of the sun over a modest area, if focused at a small enough area, can burn stuff up. You're focusing all that power on such a small area. What happens is if you have a wave, and this is the kind of tricky thing. This is the last thing we'll do. If you have a wave that is normally oscillating like that, it's zero at several specific points. If you were to plot this as intensity, where those zeros are like this, and what happens is the intensity, those points there are where the E field or B field of the light that we've talked about is zero, where the total magnitude of the wave. I tends to be like an absolute value of the wave itself. Intensity is, you've got power in a trough, just as you've got power in a peak. A trough is just merely the absence of the water. It took energy and stuff to get that out of the way. So there is an intensity involved in that. And so where the intensity is, I'm running out of paper. Where the intensity is, so zero intensity, this is the last words, is where where it's dark. Where there is no energy, there is no intensity. If there is no intensity, we interpret that as a dark spot. Intensity can be, if it's not zero, light appears. And so if you have your, well, hold on, let me think about the words of this. Let's just go with this. If the intensity is zero, there is no light. If there's anything where there's a wave, a peak, or a trough, you do see light. And what we're going to do is we're going to play with this and take advantage of it in single, double slit, diffraction grating. Polarization is a little bit weird. And then thin films is, so basically we're going to play a lot of games tomorrow with interference. And then we'll be fully ready for that problem set. And we'll have a whole weekend to do it. So that's good. That's it. Have fun in lab. And go to lab.